Greetings and salutations, magical chemists. Let's talk about the glory of buffers. A buffer is a solution that maintains a relatively constant pH if you add an acid or a base. Now, if you have a relatively constant pH, that means that you also have a relatively constant concentration of protons. Buffers have tons of applications, but they are especially important in biochemistry. Like blood, amino acids, proteins in the body, it turns out many biochemical reactions are pH sensitive, so blood is buffered. But wait, you may think, what sorcery is this? How could a buffer neutralize added acid or added base? Well, a buffer solution contains significant amounts of both a weak acid and its conjugate base. Just like always, we'll generically call the weak acid HA and its conjugate base A-. So the way that a buffer can maintain a constant pH is if you add base to a buffer solution, the weak acid will react with it. When this happens, well, you've got a weak acid reacting with hydroxide, you're going to be producing more of the conjugate base. And of course, because the weak acid is neutralizing the hydroxide, the concentration of the weak acid will go down. Oops, I realized I labeled that Cb for conjugate base. I meant to say A-. Same thing. Of course, adding an acid to a buffer solution will do the opposite. The conjugate base will neutralize the added acid, which will reduce the amount of conjugate base and produce even more of your tasty weak acid. Let's look at a visual representation of this. An ideal buffer has an equal concentration of weak acid and conjugate base, which means it's available to neutralize added base or acid. So if we add some protons, which means we're adding an acid, some of the conjugate base is going to neutralize it. And so we're using that up. But then, as that gets used up, it's producing more of the weak acid. And the other way around. If you add hydroxide, you're of course adding a base. Well, this time the weak acid is going to neutralize it, so its concentration goes down. But as it gets neutralized, it's going to be producing more of the conjugate base. It's important to recognize that weak acids and their conjugate bases make good buffers, but strong acids and bases do not. This is because, by definition, for a strong acid and base, all of their H+ and hydroxide is already dissociated into solution. It actually takes much more base to change the pH of a weak acid because you have a large reservoir of undissociated weak acid waiting around that could neutralize the base. Okay, let's go ahead and summarize what's happening when you add an acid or a base to a given buffer system. Then we'll look at some examples. So if you add an acid, the conjugate base will neutralize it, producing more of your weak acid. Now, because you have slightly more weak acid present relative to what you started with, this is going to decrease the pH of the solution, but it's only going to decrease it slightly. So a buffer solution maintains a relatively constant pH, but it's not perfect. And then if you add a base, the weak acid in the buffer will neutralize the base, and that's going to produce more of the conjugate acid. Oops, conjugate base. Now you have a little more conjugate base, so the pH of your solution will increase again slightly. Okay, next we're going to look at how to represent a buffer system using chemical reactions. You can create a buffer by combining hydrofluoric acid and sodium fluoride, because that will contain the weak acid, hydrofluoric acid, and it also, sodium fluoride is a salt containing the conjugate base of hydrofluoric acid. Remember, the sodium is 100% soluble. So a common question is to write an equilibrium reaction to describe the HF-F- buffer system. This is going to look pretty familiar to you. Let me write it out. So by convention, we always start with the weak acid component of the buffer system and add it to water. And then you show, well, it's a weak acid, that's going to protonate your water, forming hydronium, and then you get the conjugate base. So you're showing, here's the weak acid component, here's the conjugate base component, and there's how they'll convert back and forth between each other. Now, you might be thinking, wait, that looks exactly the same as the dissociation reaction you'd write if I put hydrofluoric acid in water. You're right. However, it's a buffer system because when you are starting out the problem, you of course start with hydrofluoric acid, but you also start with fluoride ions. So it's not about the equation that makes it different, it's what you're starting with. Your initial conditions, you contain both HF and F minus. Okay, here's another very common AP question. It says, write a net ionic equation demonstrating why the pH of this buffer would remain relatively constant if a small amount of HNO3 was added to the buffer system. Well, HNO3 is a strong acid, and that is important. Before we write the net ionic, let's go ahead and just write out the actual equation that shows what happens to HNO3 if you put it in this buffer solution. Of course, the reaction is going to show the HNO3, and then remember, this is an acid, so that means out of the two components of the buffer system, it's the base, F minus, that will be reacting with it. So that will produce some more hydrofluoric acid and the nitrate ion. However, remember that we want the net ionic, and in a net ionic, strong acids dissociate completely. So HNO3 isn't really HNO3, it's H plus and NO3 minus. That means NO3 minus is a spectator. So the net ionic won't show the nitrate as part of the equation. It's actually much simpler. We just have the H plus being neutralized by the F minus, forming HF. Did you notice that these arrows are completion arrows? They are not equilibrium arrows because HNO3 is a strong acid, so this is 100% going to happen. It is going to go to completion. Okay, let's try another one. But this time, we're going to write a net ionic to show why the pH is relatively constant if we add a small amount of lithium hydroxide, a strong base. Just like in the last case, it can be helpful to start off by writing the full equation first. You're not required to, but it can help you see what's going on. This time, the lithium hydroxide, because it's a base, will be neutralized by the weak acid component of the buffer, producing water and lithium fluoride. But we want the net ionic. And remember, lithium hydroxide is a strong base. It's going to dissociate 100%. And lithium's an alkali metal, so it's also going to be completely aqueous, which means that lithium is the spectator. So our final net ionic looks like this. Just the hydroxide reacting with the hydrofluoric acid, producing water and a fluoride ion. Okay, hopefully this is making sense because you're going to try a practice problem. Very exciting, I know. This time we're looking at a different buffer system. We're combining ammonium chloride and NH3 to create a buffer system containing the weak acid ammonium and its conjugate base ammonia. So you're going to do three things. You're going to write the equilibrium reaction to describe the buffer, and you're going to come up with the two net ionics that demonstrate why the pH is relatively constant, even if the buffer is attacked by an acid or a base. When you are ready to check your answers, go ahead and unpause the video. For the equilibrium reaction describing the buffer, remember by convention we always start with the acid from the buffer system. Add it to water, see what happens. All right, net ionics. Well, attacking with an acid means your strong acid, you're adding just H+, and of course it's going to be neutralized by the conjugate base, producing more of the weak acid. And when you attack with a base, it's going to be neutralized by the weak acid, producing water and more of the conjugate base. All right, that's it. Let's go ahead and move forward and talk about something known as buffer capacity. Buffer capacity is determined by how much acid and base can be neutralized by a buffer system. If you have a large capacity, then you have lots of weak acid and conjugate base present. This means large amounts of added acid or base can be neutralized before the pH of the buffer will change significantly. Of course, if you have a small capacity, you have relatively little of your weak acid and conjugate base, so only small amounts of added acid or base could be neutralized before the pH starts to change. Now you need to watch out, because if you add more acid to your buffer than the conjugate base that's present, or you add more base than the acid present, you have what they say is exceeded the capacity of the buffer. You've destroyed its buffering capability. So let's look at an example. A buffer system is created by combining 300 milliliters of 0.2 molar HNO2 and 0.4 molar LiNO2. And we want to know the maximum amount of acid that could be neutralized by the buffer system. Well, remember, if acid is being neutralized, it's being neutralized by the conjugate base. So we have to calculate how many moles of conjugate base are present. Well, let's identify our buffer system. We've got the weak acid, HNO2, nitrous acid. And then we put it with this salt, LiNO2. Remember that the lithium is 100% soluble? It's not participating in the buffering system. So our buffer system is HNO2 with NO2 minus. So the conjugate base is going to be the NO2 minus. And the NO2 minus is coming from the lithium nitride. So we need to calculate how much of our NO2 minus is present. Well, we know molarity, we know volume. We can multiply times each other and find the number of moles. I'm actually going to stick to millimoles. Remember that molarity times milliliters gives you millimoles. So this shows us that 120 millimoles, or 0.120 moles, is the maximum amount of added acid that can be neutralized by this buffer system before its buffering capacity is destroyed. I think you should take a moment and calculate what's the maximum amount of base that could be neutralized by the buffer system. And when you're ready to check your answer, unpause the video. This time, since we're trying to neutralize a base, we needed to calculate how much acid was present in this buffer. And then that, therefore, is the maximum amount of base that can be neutralized by this buffer system. Okay, these are very common questions in multiple choice, so let's go ahead and try a couple. If this is making sense, you should totally go ahead and try these problems. All three of them. We know how to do, oops, that's not what I meant to hit. We know how to do all of these problems. But if you want a little help, or you're ready to check your answers, unpause the video. In the first one, they're asking what would destroy the buffering ability of the solution, which means adding either more acid than you have base or more base than you have acid. Now, I want you to watch out for something here. When you have questions like this, it is absolutely essential to identify your buffer system. This buffer system is working with a weak base, ammonia, and its conjugate acid, ammonium. That means if you add a chemical containing ammonia or ammonium, you can't destroy the capacity of the buffer. You could only make it better. So we can eliminate two of our answer choices because one is ammonia and the other one contains ammonium. But to distinguish between the other two, we need to calculate how much ammonia and how much ammonium do we have. Well, for the base, NH3, we've got 0.2 molar times half a liter gives us 0.1 moles. Oops, I think I flipped my numbers. I'm sorry, it was the acid that was at 0.2 molar. So that means if you add more than 0.1 moles of base, you're going to destroy the buffering capacity. The base had a little higher concentration. It was 0.3 molar. So basically 0.15 moles of base, which means if you add greater than 0.15 moles of acid, you'll destroy the buffering capacity. So now we just compare these values to the values given. Notice I had 0.13 moles of an acid and 0.13 moles of a base. Well, I can handle 0.13 moles of an acid, but I cannot handle neutralizing 0.13 moles of a base. So it must be adding the lithium hydroxide that would destroy the buffering capacity. If you haven't tried the last two yet, you should, and then unpause the video when you're ready to check your answer. In the second question, you're adding half a mole of a strong base to a hydrofluoric acid and fluoride buffer system. Notice that your 0.5 moles of base is less than the 0.75 moles of hydrofluoric acid present. So adding that much base will not destroy the buffering ability of your system. However, if you add base to a system, it's basic, that means the pH is, of course, going to increase slightly. Knowing that is actually enough to answer this problem. Of course, it's also good to know that when you add the base, you are, of course, decreasing the concentration of uric acid because it's neutralizing it, and thus making more of the conjugate base in the system. And the last one was very similar to the first one. So again, you had to see how much acid you had and how much base you had. In this setup, we would have 0.25 moles of acid present and 0.15 moles of base. So we're looking for either greater than 0.25 moles of base or greater than 0.15 moles of acid. It's good to remember that if you're adding something to the buffer system that's part of the buffer system, in this case acetate or acetic acid, adding these would increase your buffer capacity. So if you look at your two remaining choices, you'll notice that we're adding 0.2 moles of an acid, but we only have 0.15 moles of base to neutralize it. So that would definitely destroy the buffering capacity. Okay, In summary, there are two requirements for a good buffer. You want it to have a large capacity, which means, of course, lots of weak acid and lots of conjugate base, but you also would prefer it to have a 1-to-1 or equimolar ratio of the weak acid and conjugate base, because that way the buffer can neutralize both added acid and added base. Just a quick reminder when you're identifying buffers. You're looking for a weak acid and its conjugate, which means they have to differ only by a single proton. So acetic acid and sodium acetate is totally a buffer. NH4 plus and NH3, also totally a buffer. But HCl and Cl- are not. They do differ by one proton, but strong acids and bases are not buffers. And then carbonic acid, H2CO3, and carbonate, even though carbonic acid is a weak acid, it's 2 protons away, and thus they're not conjugates. So that also would not be a buffer system. Okay, so here are 6 potential solutions, and I would like you to circle the ones that would make a buffer if you mixed them in equal volumes. For each one, explain why is it or isn't it? All right, go ahead, and you know what to do. Pause the video, try it, and when you're ready to check your answer, unpause the video. Well, the first one can't be a buffer. That's a strong acid. But the one below it is a buffer because you've got the weak acid hypobromous acid, and then you've got the hypobromide ion. The next one on the top can't be a buffer. You do have a weak acid, but you don't have the conjugate base. But the system below it is definitely a buffer. You have a weak base and it's conjugate acid. And then, crazy story, both of the last two are actually buffers. The one at the top is a pretty straightforward weak acid and conjugate base system. The one on the bottom, though, that's a little sneaky. You had to realize that the salt, lithium hydrogen sulfate, will dissociate producing hydrogen sulfate, which is a weak acid. And then, of course, straight up lithium sulfate has sulfate, which is the conjugate base. Okay, so for our very last practice problem, it says choose a 1-to-1 buffer from the buffers you circle above. Well, remember that we said we mix them in equal volumes? So for a 1-to-1 buffer, they'd also have to be equal molarities. Out of all the circled buffers, there is only one. So you should totally try to write an equilibrium reaction to describe this buffer and a net ionic to show how it will neutralize the addition of added hydrochloric acid. However, there's a couple of sneaky little things built in there too. You are welcome to try them, but we are going to go over them as soon as you've written out your equilibrium reaction and net ionic. So when you are ready to move forward and check your answers, unpause the video. Remember, the equilibrium reaction, by convention, starts with the weak acid. For the net ionic, we're adding a strong acid, so it'll be neutralized by the conjugate base. Now, there is a part of question, or part A, that I skipped. It said, what is true about the weak acid conjugate base ratio? Remember, we specifically chose a 1-to-1 buffer. That means the ratio of weak acid to conjugate base has to be equal to 1. So if you wrote it as a fraction, took the number of particles of your weak acid divided by the conjugate, it would be equal to 1, because there's 1 for every of the other. Okay, and then the very last question says, after we added that acid, like we did in part B, what happened to our ratio? Well, remember the acid was neutralized by the conjugate base, which means some of the conjugate base is getting used up. And when that happens, you're making more of your weak acid. So hopefully you can tell that this means the ratio is now going to be greater than 1. And there you have it, the fun and excitement of buffers. So thank you for playing with the glories of chemistry.